क्या क्या देख रहे हैं? क्या बोल रहे हैं? मुझे खुद सुना था ना, डैडी कॉलिंग। डैडी बनाने लगे।
I guess we can start now. Am I audible and is my screen visible? Hello? Okay. I hope my screen is visible too. Do you have a doubt, Sudhansh? Okay. Hello everyone and welcome to Module 5 of the Fundamentals of Astronomy by Kritika. Our today's topic is the cosmic distance ladder. To start off, we have a pretty massive problem. When we look up at the night sky, we have absolutely no perception of depth. A tiny meteor burning up in our atmosphere looks exactly the same as a giant star much far away. They'll just look like tiny dots of light. Which leaves us with the question, how do we measure the infinite? The answer is by a chain of overlapping rungs. We don't measure deep space directly because we simply just cannot. We start close to home, figure out a local distance, and use that as a ruler to measure out the next, like a ladder. But we need to be very careful because every single rung relies entirely on the one beneath it. If our math for the very first step or a step below the one we are currently doing is wrong, the errors stack up exponentially. Let's walk through the entire process. It all started in ancient Greece. Our very first step was figuring out the size of Earth, which was done by Eratosthenes by using nothing but shadows. He knew that in the city of Syene, on the summer solstice, the sun was perfectly overhead and did not cast a shadow. But in Alexandria, just for your reference, this is Syene and this is Alexandria. They both lie in the present day Africa. And as you may notice, Syene lies on Tropic of Cancer. In Alexandria, where Eratosthenes was, a stick in the ground did cast a shadow. he measured the angle of that shadow and found that it was 7.2 degrees. Since 7.2 degrees is exactly 1/50th of a full circle, he knew that the distance between those two cities had to be 1/50th of the Earth's total circumference. Now, by finding the distance which he set out a graduate student to do so, and doing the math, he figured out that the Earth is roughly 40,000 kilometers around. Now take a look at this math. If we divide that 40,000 kilometers by 360 degrees, we can figure out that 1 degree of latitude equals 111 kilometers. I know that this is a brief detour into geography, but we find that by moving 1 degree latitude wise, we cover 111 kilometers on ground. This is just one of the applications of our findings. Anyways, coming back to our topic, we now have the circumference of the Earth. We use this to find out the distance between the Earth and the Moon. During a lunar eclipse, Aristarchus observed that the Moon takes three and a half hours, factored in for all the errors, to cross the Earth's shadow. Let's understand his calculations. We know that the orbital period of the Moon is 28 days. Since the Moon has a constant speed, we can take the ratios. 28 days for an entire lap, which is 2 pi times distance of Moon, and 3.5 hours for crossing the Earth's shadow, which is roughly how wide the Earth actually is. Upon solving, we get that the Moon is 61 times the radius of Earth far from us, which from our previous finding is roughly 388,000 kilometers. Using the present day methods, the calculated distance is about 384,000 kilometers, which means Aristarchus, 2000 years ago from now, got the distance almost spot on. Let's take a brief pause at the ladder to look at how we figured out the height of Mount Everest. We choose two observation points. I don't know why the point A has gone off the screen, but point B and point A, you can extrapolate it from here. We choose two observation points separated by a known distance called a baseline. From each point, we measure the angle to the mountain peak. With one side and two angles known, the trigonometry allows us to calculate the distance of the mountain like so. This technique is known as triangulation. It was used extensively in the Great Trigonometrical Survey of India, where distant Himalayan peaks were measured using careful angle measurements and geometry. Let's now apply this to astronomy. Johannes Kepler figured out the orbital ratios of planets. Like Venus orbits at about 0.72 times Earth's distance from the Sun, and Mars, for example, at about 1.52 times Earth's distance from the Sun. But we still did not have the hard numbers in kilometers per se. We needed a baseline for the entire solar system. For our convenience, we set it to be the astronomical unit, or the AU, defining it as the distance between the Earth and the Sun. To get this, astronomers first used the whole Earth as a baseline. During the 1761 and 1769 expeditions, they sailed across the world to watch Venus cross the face of the Sun. Let's take a quick dive into history. All this was going on right in the middle of the 7 Years' War. So, astronomers dodged pirates, naval battles, and diseases just to measure this. Because they watched from opposite side of the globe, Venus looked like it had slightly shifted against the Sun. That visual shift, combined with the distance between the observers, gave us the math to calculate the actual distance to the Sun. If you are interested in the maths, here's what's going on. We collected the data from various points on the globe to be able to set up this entire system. These both angles will be equal, so we can equate the ratio of small d and the distance between Venus and the Sun with capital D and the distance between Venus and the Earth. These, by the way, 0.72 AU and 0.28 AU are Kepler's givings. I will share this video if you are further interested in finding out how we calculate small d. This calculation finally gave us the astronomical unit to be 1.496 times 10 to the power 11 meters, or about 149 kilometers. Once we had the astronomical unit, we could use the Earth's orbit as a baseline to reach the stars. This is basically the triangulation method that we saw for calculating the peak of Mount Everest. Triangulation applied to astronomy is stellar parallax. We take a picture of star in January, wait for 6 months, and take another in July. The Earth now has moved 2 astronomical units across its orbit, so nearby stars look like they have shifted against the distant background. The distance of the star from Earth, then, is just 1 AU over the tangent of the parallax angle. Parallax angle is calculated is, this is the parallax angle. 1 AU, 1 AU, so total of 2 AU. We wait 6 months to take separate pictures. We can further use the approximation that the tangent of a very small angle theta is just theta, given that it is in radians, to get 1 arc second to be equal to 1 parsec. 1 degree is equal to 60 arc minutes, and each arc minute is equal to 60 arc second. So 1 arc second is just 1 over 3600 degrees. Parsec is the natural unit of stellar distance. 1 parsec is equal to 3.26 light years. Today, we use satellites like Gaia to measure these microscopic shifts from space. But there is a hard limit to it. Eventually, the stars are just so far away that the shift is too small to be measured precisely. So we again have to switch our methods entirely. Am I audible? Hello?
Yes.
Yes.
Okay, because someone in the group said that. Okay, I'll continue. So we again have to switch our methods entirely. We started our calculations with basic shadows in ancient Greece. Moving on to using basic maths and observation of lunar eclipses, followed by applying triangulation to astronomy, and now we move on to the next method. The idea is very simple. If we know exactly how bright a light bulb truly is, we can figure out how far away it is just by seeing how dim it looks from the Earth. Standard candles is a term for any object of known luminosity. Examples include Cepheid variables, Type 1 supernova, and RR Lyrae. Let's first try to break down the math behind it, and then we will actually get back to it. Historically, astronomers ranked stars from magnitude 1 down to 6. Norman Pogson realized that this 5 magnitude difference, that is 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6, is exactly a factor of 100 in flux. Flux is basically the energy received per unit area per unit time. If you do the math to find the jump for just one magnitude step, it's the fifth root of 100, which is about 2.5. So every time a star drops one magnitude, it is 2.5 times brighter. Assume two stars and let M1 and M2 and F1 and F2 denote the magnitudes of the fluxes, denote the magnitudes and the fluxes of the two stars respectively. We can calculate the flux ratio like this, and we perform some basic algebra like taking log and multiplication. This is too basic, to finally arrive at the Poggen's equation. M1 minus M2 equals minus 2.5 log F1 upon F2 to the base 10. We now use this equation and substitute the flux formula. F is equal to luminosity, which is basically just the energy radiated, over 4 pi d square to get the distance. But before substitution, we define two terms, apparent and the absolute magnitude. Apparent magnitude of a star is just the magnitude of the star as seen by us on Earth, where the star truly is, which is the star being at a distance d from us. Absolute magnitude, on the other hand, is the magnitude of the star when it is hypothetically placed at a distance of 10 parsecs away from Earth. We do the math to arrive at this equation. This is all just basic math. And we finally get this equation. Small m minus capital M equals 5 log d to the base 10 minus 5. We coin the small m minus capital M to be the distance modulus. And all we need to find the distance d of a star from Earth is to find the absolute magnitude, because the apparent magnitude is something that we can calculate, that we can actually find using our observational tools. We can determine the absolute magnitude of Cepheid variables thanks to Henrietta Leavitt's discovery that a Cepheid's pulsation period is directly related to its intrinsic luminosity. By simply observing a Cepheid over time, we can measure its period, the time it takes to complete one full cycle of brightening and dimming. Let's first understand why Cepheids do this. To understand this, we first need to take a look at where they sit on the Hertzsprung-Russell diagram. This diagram basically just plots a star's luminosity against its temperature. The blue line represents the main sequence, where most stars, including our sun, spend the majority of their lives in. Cutting across the diagram is a narrow region known as the instability strip. As you may notice, both the Cepheid variables and the RR Lyrae lie inside this band. Cepheids occupy this region because conditions inside the star become unstable. Here, partially ionized helium acts almost like a wall. As the star contracts, helium traps heat, increasing the pressure inside the star. The pressure in turn pushes the outer layers outward. As the star expands, the helium becomes more transparent, allowing heat to escape. The pressure then drops again, gravity takes over, and the star contracts again. This repeating cycle of expansion and contraction produces regular pulsations we observe. The larger and more luminous the Cepheid is, the longer this cycle takes to complete. This leads directly to Leavitt's discovery. When she plotted the pulsation period of Cepheids against their luminosity, the points did not scatter randomly. Instead, they fell along a well-defined line. This means that if we measure a Cepheid's period, we can immediately determine its intrinsic luminosity or absolute magnitude. The Large Magellanic Cloud, or the LMC, is a satellite dwarf galaxy of the Milky Way, and Henrietta Leavitt's discovery and Leavitt discovered her law while studying Cepheids in the LMC as a part of the Harvard computers. Unfortunately, she wasn't recognized for her work as she was a woman. Feel free to look it up if you want to find out more. This was my part of the presentation. I will now hand it over to Ayushi.
Thanks, Ishan. Give me a moment. I'll share my screen.
I guess till the time she shares her screen, I'll just answer the doubt. So someone had asked, like, is there a specific reason for 10 parsec? So the reason that I can think of is, first of all, it simplifies the calculation a lot because we are taking log as in the base of 10. So it gives us the clean and simple term 5. And also taking a larger number means that the star is so far away from us that our telescopes at that time were not able to observe the stars perfectly. So yeah, that's the reason that I can.
Is the screen visible? Am I audible?
The screen is
Am
not
I audible?
visible, but you are audible.
Okay, just a second. Is it visible now?
Uh, your screen is not visible even though you are audible. So I think it's not a net issue. Maybe try sharing the screen from another device.
Fine, just a second. Is it visible now?
Yes, your
Yes, it
screen
is.
is visible now.
I start. So you might have wondered why the graph in the previous slide contained 2 lines instead of one. Well, it turns out that not just for Cepheids, but for all stars in the Milky Way, scientists observed some population classes. Population 1 stars are young and rich in metals. They're found in regions where stars are actively forming, such as open clusters and spiral arms, found in the galactic disk. Now, the Milky Way is a spiral galaxy, and the disk is the flat, rotating part of the galaxy. It consists of the major spiral arms and most of the stars, and the gas and dust and everything. Now, population 2 stars are old and metal poor. They're located in the galactic halo, which is the enormous, diffuse, approximately spherical region surrounding the disk and the central bulge. Now, the stars in this region have inclined and eccentric orbits. The halo now mainly contains globular clusters, which are groups of such very old stars bundled together. For your information, such groups of type 1 stars present in the galactic disk are called open clusters. Also, there was an article I came across some time back that suggested that the stellar halo might be tilted and oblong instead of spherical, as I mentioned earlier. So, in case you want to check that out, I'll send the link on Teams after the session. Now, it has been hypothesized that population 3 stars exist as well. And they're supposed to be extremely massive and luminous and hot stars with virtually no metals. They're likely to have existed in the very early universe, and they might have been the ones where the production of chemical elements heavier than hydrogen started in the universe. Now, type 1 Cepheids are population 1 stars with high metallicities, and they have shorter pulsation periods, that's typically less than 10 days. Type 2 Cepheids, on the other hand, are population 2 stars with a low metal content and pulsation periods between 10 and 100 days. So, in a nutshell, you observe a Cepheid star over several nights and measure how long it takes to go from bright to dim and back to bright again. Your observational data will give you the apparent magnitude of the star. The period gives you an idea of what population it belongs to. So now you can use Levitt's plot to find M, the absolute magnitude, and then you can use the standard candle distance modulus relation to find the distance. Now, this method allows us to measure distances across and beyond the local group. Now, what's the local group? Turns out the galaxies exist in clusters. And these clusters themselves are nested within bigger clusters and so on. So there's this naturally formed hierarchy in which the universe is structured. Now you might ask, why are there 2 superclusters? Well, that's because the Virgo supercluster was named first. And we later discovered that it was a smaller part of Laniakea, which was defined somewhat differently based on a larger scale criterion. So both names remain useful because they describe different scales and use different definitions. Feel free to look these up if you want to delve deeper. Let's look at one more standard candle that helps us extend our reach, supernovae. Before diving into the mechanics, you should know a little about how they're classified. Astronomers classify supernovae according to their light curves and the absorption lines of different chemical elements that appear in their spectra. Now, if a supernova spectrum contains the Balmer lines of hydrogen, it is classified as type 2, otherwise it is type 1. In each of these 2 types, there are subdivisions according to the presence of lines from other elements or the shape of the light curve. Now, the light curve I just talked about is just a graph of the supernova's apparent magnitude as a function of time. So we basically classify them on a mixture of criteria that are their brightness and their spectral composition. A supernova type 1a, SN1a in short, is among the brightest type of ordinary supernovae. And one way for these to occur is in a binary system, where 2 stars orbit their common center of gravity. And one of them is a carbon-oxygen white dwarf, which is a remnant of a star. So if the stars orbit close to each other, the gases and plasma in the outer layers of the other star is drawn into the white dwarf due to its gravity, as the animation showed. As its mass grows and it approaches the Chandrasekhar limit of about 1.4 solar masses, the high density and temperature can trigger a runaway carbon fusion that destroys the white dwarf and expels its material outwards. Now, since the basic mechanism by which they arise is the same, all SN1A have the same absolute magnitude of about minus 19.3 at maximum light. Now we can measure the apparent magnitude from Earth and plug in its peak value into the distance modulus relation to find the distance from that supernova. This method helps measure distances from about 1 megaparsec to over a gigaparsec. By the way, it was by comparing this apparent brightness with the redshift for these supernovae that the accelerating expansion of the universe was discovered in 2011. And the existence of dark energy was proposed to solve the paradox that everything in the universe should ideally come closer over time due to gravity, but that's contrary to reality. Let's move on to the Tully-Fisher relation, which is a characteristic of spiral galaxies. This relates the intrinsic luminosity of spiral galaxies with the rotational velocity of their gas or stars. Now, luminosity is the total power output of a star, so it is synonymous with brightness, which is proportional to some power of the mass. For main sequence stars, it is observed that this power is approximately 3.5. Now, rotational velocities are measured by observing the spectrum, specifically the hydrogen line that has a wavelength of about 21 centimeters. The rotation of the galaxy causes the hydrogen line to be Doppler shifted. Now, imagine a rotating spiral galaxy at an instant. Now, just as the end moving away from us will be redshifted, and the end moving towards us will be Doppler shifted towards the blue end of the spectrum. If you analyze one end as the galaxy rotates, it will periodically be redshifted and blue shifted. And the time between two redshifts or two blue shifts will be the time period of rotation of the galaxy. Now, when you look at the hydrogen spectrum, the light coming from hydrogen atoms in the near end will appear blue shifted. But as that end moves away, it'll start shifting towards the red. Similarly, the light coming from the far end will initially be red shifted, but it'll start shifting towards the blue as that far end comes towards us. And they will keep exchanging positions in this manner in sync with the rotation of the galaxy. So we can use this to directly find the radiation velocity. When your detector looks at a galaxy, it measures the flux coming through it. So if you know the distance to the galaxy, maybe with the help of a standard candle or using any other methods, you can easily find the luminosity. Because flux is related to luminosity as flux is equal to luminosity by 4 pi distance squared. Now the hydrogen spectrum analysis gives you the rotational velocity, and we can plot the log of the luminosity against the log of the rotational velocity, which gives us alpha. If you remember 2 slides ago, L was proportional to V rotational raised to alpha. So if you obtain this plot, and if we have the rotational velocity, we can use it to find the luminosity, which will give us the distance to a given spiral galaxy. Now, let me take you through how data is collected and analyzed in real life. SBF, short for surface brightness fluctuations, is a technique used to measure distances to galaxies with high precision. It is based on the observation that closer galaxies exhibit more visible fluctuations in brightness due to the distribution of stars between them. Now, before understanding this, let me tell you what a CCD is. It stands for a charge-coupled device. It is a digital sensor that captures light and turns it into pixels. So it just acts like an electronic film for cameras. Now, what you need to do is analyze the pixel-to-pixel variations in the surface brightness. And this helps us to measure individual distances at less than 5% precision. The entire concept behind this is that the physical area of a galaxy projected onto a single pixel grows as the galaxy moves further away. So to understand this, imagine a grid of pixels and two galaxies, one at a distance d and the other at 3d. A CCD pixel captures light from a fixed angular area on the sky. So this is basically a tiny solid angle. So when you look at a nearby galaxy at distance d, that fixed angular pixel covers a certain physical area on the surface of the galaxy that is visible to you. But if you look at the galaxy which is at a distance, say 3D, now the angular size of the pixel is going to stay the same. So the physical area of the galaxy that a single pixel covers increases by 9. Because that galaxy looks smaller to you. But the solid angle subtended by a single pixel is still the same. So the physical area of a galaxy sampled by a single pixel is directly proportional to the square of the distance. So the number of stars per pixel turns out proportional to the square of the distance. And the pixel to pixel fluctuations, that is how grainy the image is, that changes as the distance of the galaxy changes. In the earlier slide, when you looked at the smooth image on the right versus the grainy image on the left, you're seeing this statistic in action because a nearby galaxy has fewer stars per pixel. And a distant galaxy has so many stars per pixel that they average out smoothly. So the grainier version has more noise. Now, once you have this fluctuation weighted luminosity, you can convert it into a standard astronomical absolute magnitude using Poisson's relation. Let me show you how this equation is actually derived. So, I hope this is visible. This is a handwritten page. Okay, I'll assume it's visible. Yeah, thank you. So firstly, consider that all photons have the same wavelength. This simplifies our analysis, and then we can do something about it, which I'll tell you in the end. Now, since the energy is constant, imagine this, the flux represents the number of photons that hit a unit area A, a distance d away at time t. So the probability that certain photons hit a unit area from a distance d away at a time t is expressed as this. How did this come about? The numerator is flux. That makes sense. And the denominator, you have to take an average over the total number of photons that you receive. This is not a time average. Don't confuse it with that. This is a number average. Now, the effective luminosity is something we define as the luminosity average over all the hits. And the luminosity is defined as flux into distance, into 4 pi times distance squared. Now, the key shift in perspective is that we're not averaging luminosity over time. I'm placing emphasis on this. We're averaging this over the number of photons, the count of photons that we receive. And that's where this expectation value comes from. So this is the average number of hits, average number of photons that hit a unit area. I hope that clears it up. I'll move back to the PPT now. Yeah. Okay, now this equation for the apparent magnitude has some terms. I'll elaborate on them one by one. So a data number, first of all, Dn is a data number, and exp time represents the exposure time, and zp is the 0 point. Now, first of all, the data number. The camera or the detector's computer reads the charge that's collected on the camera. So this is a CCD, right? So this works on the principle of charges. So light hits a film and charges get distributed on it accordingly. Now your detector's computer will read that charge and convert it into a number, the data number. So a low data number means that the pixel is very black, pitch black, and a high data number means it's completely white or saturated. And everything in between is a different brightness. So it's sort of grayscale if you think about it. In standard photo editing software, you might see this referred to as ADU, which is short for analog to digital unit. But it's sort of the digital language that your computer uses to map out the light that your sensor captures, the pattern of light that's captured. Now for the EXP time, typically astronomic photos are not instantaneous. You have to put your camera or your detector at a place, at a dark place that is, for a very long time. And that is called the exposure time. And it takes shots of the sky for like a very long time. So EXP time is just that exposure time. And then the 0 point. So a 0 point is something that you use to calibrate a detector and to standardize your result. So this is basically because every camera is different. You might have noticed that in older cameras, your image inherently appeared a bit white, noisy, or too bright. So to negate the effects of changing detectors, because this is a scientific result, you want to align your observations with your theory. So you have to negate all interruptions that come due to variations in experimental observations taken at different places by different people using different detectors. So 0 point basically does that. Now it's defined in a certain way that if you have a star at a distance of 10 parsecs, then the value you get is called a 0 point. It's basically the magnitude of an imaginary star that would produce exactly 1 count per second. So the 0 point is related to the data number now. The data number, by the way, is measured in counts per second. So the magnitude that you get, the value of small m in the formula here, of an imaginary star that produces a data number of exactly 1 count per second on that specific detector setup. Now, if an object produces exactly 1 count per second, that means its apparent magnitude is exactly equal to the 0 point. Now, on an ending note, let me introduce you to the Hubble tension, one of the biggest major unsolved problems in astronomy. As we all know, the universe is expanding, contrary to our initial expectations. And we introduced the concept of dark energy to explain this. But the problem is that two different, highly precise methods of measuring the expansion rate of the universe give conflicting results. To understand this, you have to know the basic expression of Hubble's law, which is V is equal to h naught by d. Here, h naught is the Hubble's constant that measures the rate of expansion of the universe. D is the distance of a given celestial body, and V is the velocity. So this entire expression is essentially a measure of what you would call redshift, and that indirectly leads you to measure the expansion of the universe. Now, we tried to find the value of Hubble's constant using two methods, as I mentioned earlier. The first one was by looking at nearby objects like standard candles. We ran an analysis and we found it to be 73 kilometers per second. But we used another method simultaneously. We looked at the cosmic microwave background, which is essentially the leftover radiation from the Big Bang. And that gave a Hubble constant value of 67 kilometers per second. Now, in such a scenario, if one of the measurements would have had a massive margin of error, we could have been satisfied with the other. But the issue is that as time progressed, both measurements have become incredibly precise, and it's difficult to refute one of them. So we have two measurements of the same physical quantity, and that suggests a gap in our understanding of the universe. I'll leave you to think about this. And we reached the end of our presentation. I will upload some links that you can check out if you're interested in topics like the Hubble's constant, the Hubble tension, CCDs. So if you find time, you can check them out. That's it. Thank you so much. Also, if you have any doubts, feel free to ask them right here. So the hydrogen line we saw in the type 1A supernova was the 21 centimeter line. That was the wavelength of the hydrogen line we saw. I hope that clears it. No, it's part of the Balmer spectrum, the visible spectrum of light that you see. 21 centimeters of wavelength. It's visible to you. Yeah. Anyone else? Okay, wait, I'll share the screen. Yeah, so the concept is that you have variant detectors. I hope you understood this, that some detector inherently has a quality of the image that it produces. Um, so you might have observed in older cameras, the image looked somewhat brighter or duller. It's all about the brightness of the image. So to standardize this, so that if if you take if you take measurements using two different detectors, two different cameras, you don't want the difference to show up in the theory, in your equations. So that's why you introduce this to standardize your theory and to reduce to eliminate this dependence on detectors. Now, you you need an imaginary star that will produce a data number of exactly 1 count per second. So if you compute the data number of each pixel and average it out, you would get the number 1 on that detector. And mind you, this is an imaginary star. You're imagining this. So if such an imaginary star produces exactly 1 count per second, that means its apparent magnitude is equal to the 0 point. You're considering this for an exposure time of 1 second. That's why you got 1 count per second. So the term within the log, it becomes 1. So the log term becomes 0. And you're left with m is equal to 0 point. So I think that's it. I hope it cleared it up. Just let me know if you have anything else to ask about this. Yeah, so it's different for every detector, every camera you have. There's a different value for that. And you have to put it into this equation before you do any further calculations with the apparent magnitude that you obtain. Yes, it's detector specific. That's why. It's like you calibrate your detector, but then you can't calibrate a detector. So you have to put that into your equation. Yeah. Yeah, so all supernovae have, yes, that's correct, 19.3 with an error of 0.3. I mean, what do you need me to clarify in that? All supernovae of type 1a. This is a subtype of type 1 supernovae, one of the brightest ordinary supernovae. Is that your doubt? Yes, all of them. All of them have, that's why this method is valid. That is entirely why this method is valid. You're able to get a fixed value of the absolute magnitude, which is this 19.3, and then you sit on Earth and your camera takes the flux, yeah, minus 19.3. So you sit on Earth, your camera takes the flux, you find out the apparent magnitude from that, plug it into Poisson's equation, and you get the distance. So yes, this absolute magnitude is fixed at 19.3 for all supernovae of type 1a, but there's a catch. I don't think I mentioned that, and I'm really sorry for it. But this graph shows it really well. I think I forgot to mention that. The Now a supernova obviously has a fluctuating brightness because it's essentially material expelled out from a star and spreads all throughout space. So there comes a point when the supernova has maximum brightness, the peak of this graph that you see in the slide. So that max brightness is what you should measure as your apparent magnitude. And the absolute magnitude at that peak is minus 19.3. And then you measure the apparent magnitude at the peak and then plug both the values into the equation. So you get that. I hope that's clear. Are there any more doubts? If there are no more doubts, then maybe we can end the meeting. If you have any further doubts, feel free to post it on the group. They'll be clarified there. So, thank you so much, Epi.